Welcome to our deep dive into one of the most fundamental concepts in data analysis, statistical variance. Understanding this metric is crucial for making reliable data-driven decisions. We begin by exploring the idea of variation itself, the foundation of all statistics. Variation is the heart of statistics. The greater the variability in your data, the greater the uncertainty in any estimates you make from it. One simple way to measure variation is the range, which is the difference between the maximum and minimum values. However, range is highly sensitive to outliers, limiting its usefulness. To improve our measure of variation, we need a better method to quantify how spread out our data points are. A more robust approach is to measure how far each data point deviates from the mean or average value. By squaring these deviations and summing them up, we arrive at the sum of squares. This calculation, represented by the formula sum of y minus y bar squared, is the foundation of statistical variability. Next, let's look at the crucial concept of degrees of freedom, often abbreviated as DF. Degrees of freedom are calculated as the sample size, denoted by n, minus the number of parameters you estimated from the data key. For instance, in simple linear regression, where we estimate two parameters, the slope and the intercept, degrees of freedom equals n minus 2. In a one-way ANOVA with 5 groups, you would use n minus 5 feet. Now we can combine these concepts into the primary formula for variance. Variance, symbolized as s squared, is defined as the sum of squared deviations divided by the degrees of freedom. Specifically, this is the sum of squares divided by n minus 1 foot. We divide by n minus 1 foot instead of n because we estimated the mean from the same data set. This adjustment provides an unbiased estimate of the population variance. Let's illustrate how variance works with a practical example using a baseball league scenario. Consider League A and League B. They have different average scores, or means, but when we run the variance calculation, they both have an identical variance of 1.33. Now compare League B and League C. They share the same mean, but League C has a drastically different variance of 14.22. This demonstrates a much wider spread in the scores. This practical example leads us to the crucial point of why variance is so important in statistical analysis. Large differences in variability, or variance, between data sets significantly affect the reliability and interpretation of your results. When variances differ substantially, comparing the means of two groups becomes statistically risky because the variability itself might be the most important finding.